Morning, guys, and welcome to Physics 101. Do you guys hear me? You can type if you want to. Okay, very good. Thank you very much. Thank you, guys. Okay, so today we are actually in week 2. Last week we kind of started because of the fact that we have that holiday. So it was a little bit, we did half the things we're supposed to do on week 1. So today the plan is to finish that, and then we start the second part, which has to do with sound. Today also at 12:45, we have lab, and lab is a live session, okay? Lab is a live session. That means today at 12:45, I'll see you in room 214 on the second floor of the physical science building to do the lab. The lab has to do with the speed of sound. So hopefully we're going to cover at least the idea behind that lab before we finish the class today. So that is the plan for today. So I also have added some resources to your week 2, basically Canvas resource, basically under model of week 2, and that includes a PowerPoint, basically a summary of the topics. Now, the textbook that we're still using Kirkpatrick, but the PowerPoint basically is a little bit done differently in a sense that it follows the ideas that are covered in this unit, but it's still, you have it there. Also, you have a lot of videos. I think you have a set of 4 videos. Each and every one of them is about 4 minutes long. Probably some of them are less, maybe one of them is more. But the idea here is that you take your time to watch those videos. And as you do, take notes. They're short videos, so you should be able to do that. And as you take notes, basically the topics that are covered and so on and so forth, after you finish all of those videos, which are short videos, total of less than 20 minutes altogether, then you're supposed to go into the quiz, which has several questions. I think it's like 5 or 6 questions. So you take that quiz based on your understanding. Now, the combination of the book, which is chapter 15 and 16, and the combination of the PowerPoints that you guys have it, and those videos, they should be able to get you with that quiz. Now, the quiz has 2 attempts. If you don't score 100% of them, in other words, if you don't answer all of those 5 questions correctly, don't take the quiz immediately. Go back, see the ideas that are covered. The quiz covers the same question, so it's not like a random number. It's not going to be different from the first time around. So just make sure you understand the topics that are covered in those videos, the things that you really need to review further. For example, I don't understand what is a frequency. I don't understand how the frequency and the wavelength are connected to one another, and so on and so forth. Is the speed of sound the same everywhere, or does it differ from a medium to medium to medium? Those are the topics that are covered in the quiz. So you go back, review the materials, ask questions if you want to, and we should be able to go through them, then take the quiz again so that you score 100% of it. The point behind the quiz is to help you, basically guide you in your learning, at least for these topics. So that is the plan. We also have a discussion item at the bottom, so you guys go through it, similar to the one that you have that is due this weekend. This is for week 2. Week 2 is more specific to the topic. Again, you go and answer the quiz, review your peers' comments or postings, discuss with them, so that you're interacting with the materials. Remember, all of these things are graded, and all of these things are going towards your overall grade. So please do not take these things lightly and fork with them. Spend the time that you're supposed to be learning on them by sitting in this session, asking questions in the live sessions, and also going home and doing the reading. I mean, you're home, but you do the readings and do the videos. Sounds good, everybody? Okay, thank you very much. Okay, so let me get into my notes from last time, and then I will share the screen with you guys. So again, we're still covering the topics that has to do with the chapter 15. By the way, the lab on chapter 15 is supposedly on chapter 16, but it's more actually on chapter 15 than 16. The relationship is on chapter 15, but the concept that is being explored is from chapter 16. Let me explain. So let me tell you first of all what the lab is. Oh, I need to change the color. So the lab is basically deals with this relationship that we're going to explore. The velocity of the wave is equal to the wavelength times the frequency. We just introduced the frequency, but for the case of oscillations that we did last time. So a frequency is how many times, for the case of the spring, for example, how many times does spring go up and down per second. That is what the frequency is. So if it goes once up and down in every second, then the frequency is 1 oscillation per second. If it does go up and down in 1 second, then the frequency in this case is 2 oscillations per second. If it does 100 times going up and down so fast, that means it's 100 oscillations per second. But if it takes, by the time 1 second expires, it only does half an oscillation, then it's in this case half an oscillation per second. So depending if it's going very fast up and down, then the oscillations, the number of oscillations per second will be high and the frequency will be high. If it's going slow, then the number of oscillations per second are going to be less and the frequency is going to be less. And an idea that we covered last time also has to do with the time it takes to go 1 oscillation, and that time is a period. So if all I am interested is just 1 oscillation, I don't care about 1 second. I just want to know how long does it take for 1 oscillation. Again, the time it takes to go for full oscillation, that is a period. If it's 1 second, that means in every 1 second I have 1 oscillation. In this case, the frequency is also 1. So that is the relationship between the two. And the idea that we explored last time is the period times the frequency is always 1, no matter what you do to that product. So if I give you the frequency, then you should be able to find the period, and vice versa. All you have to do is invert the other one, basically take the inverse of it. So if the oscillations is 1 second, if the oscillations take 1 second, then the frequency in this case is 1/2. If the oscillations take 100 seconds, then the frequency in this case is 1/100, which is 0.01 oscillation per second, 100th of an oscillation per second, and so on and so forth. So that is a relationship that we identified for the mass spring system. Also, the other example that we talk about often is the case of the pendulum. And the pendulum also is similar in a sense to the mass spring system, except in the case of the pendulum, what you have a mass, or a bob it's called actually, that is suspended on a string. So this mass in here is taken off of its equilibrium position and let go. So the length of the string is L, and you let go of it. So it's going to do, in this case, it's going to go up to the opposite direction and then come back and then return. The time it takes to go this way and come back is also a period. So that is the period T. Again, I could ask how many oscillations does the pendulum does in 1 second, and that is going to be the frequency. So the frequency in this case is also inversely proportional to the period. So those are some of the concepts that we're exploring. Here, in the case of the mass spring system, this is a useful relationship to know for the case of the mass spring system. The period is related to the mass of this object and the spring constant K. So that is going to give me a period that is equal to T is equal to 2 pi. That is, pi is a number. So this is 6.28. 2 times pi is 3.14. When you multiply it by 2, it's just 6.28 times the square root of, and in this case, it's m over k. M is the mass of the spring. The mass of the mass that is suspended. So that is mass m, and the spring has a spring constant k. So those are the properties. So this is the mass, and this is the spring constant. All of this have more details in the book. So there is an explanation of this formula, and it's actually on Canvas. Again, if you have difficulty with these things, please let me know. In a similar fashion, the period. So this is the period. So if you're curious, trying to know what the frequency is, the frequency is just the inverse of that. So you just take, instead of multiplying by 2 pi, you invert that, and you invert the inside in here, so it's going to be k over m. Okay, k over m. So that where k is the spring constant, so it's just the inverse of everything. Square root is square root. The same thing in here. The period t is equal to 2 pi square root of, again, the length of the string. So this is the length of the string. L divided by the constant of the universal gravity. I know we're going to explore this idea later on further, but this is a constant. It doesn't change. On Earth, it's 10 meter per second squared divided by g. So the g in this case is constant. It doesn't change. Okay. You will see me sometimes use the value of 10. And in this case, the reason why I'm using the value of 10, it's because of simpler calculations, because 9.8 is close from, so it's not exactly equal, but approximately equal to 10. So when we're doing calculations, it's much easier to multiply by 10 and divide by 10 rather than having to have that 9.8, which is sometimes hard to do the calculations with it. So this is just for a purpose of calculations only, of ease of calculations, I should say. Real value on Earth, we take it to be 9.8. And it really depends on your location. So we're going to explore this idea further down the road, but this is a constant. So the only thing that really controls your spring and your pendulum, this is called the pendulum, by the way, is the length of the string, because that's the only thing that you can control. So in other words, the mass in here doesn't matter. You could put a small mass, you could put a big mass, but it doesn't matter. It matters only in one thing, and that is it needs to really to keep the string stretched. Okay. Of course, this not stretched. Yeah, it should not really be too light so that the string can crumble basically on the way through, because then the length changes, and if the length changes, the time also changes. So again, the frequency is just the inverse of this number. So if you're curious trying to find the frequency, it's just 1 over 2 pi square root of g over L, where you invert everything. Okay, so this is some of the relationships that we're going to be using. So these are some of the ideas that we're considering in here. These are coming from oscillations. I mean, yes, oscillations. And the difference between an oscillation from our last discussion is an oscillation is localized. Meaning, if I take the pendulum, it's just swinging back and forth, back and forth, back and forth in my location. It's not going anywhere. The same thing for the mass spring system. It's just going up and down, up and down, up and down, not going anywhere other than that, okay? So it's not going the entire room, if you wish. And like sound, which is propagating from the source to the receiver, and from the receiver, it's basically going through the medium. So that's a case of sound. Light, for example, also is a wave, and light travels from the source, which is the light source, and covers the entire space that you give it to. I mean, as it goes around, it's going to weaken, because a light bulb, for example, that is very far away is not as lit as, for example, a light that is nearby. And that is expected, because the propagation also comes at a cost, namely the distance drops the intensity of the light in that case. And same thing for sound, by the way. If you're close from the source of sound, it's loud, and as you move away from it, it becomes weaker and weaker. So that is also part of the property. So again, what is a wave? A wave is an oscillation, A-N, not O-N. An oscillation that travels in a medium. So what I mean by medium, I mean air, for example, for the case of sound, okay? By the way, sound also travels not just in air, travels in a lot of media too. For example, on the floor, in the water, it travels on the ground, travels in all kinds of places. Okay. For example, a seismic wave, which is an earthquake, starts in the inner depth of the earth, and that actually takes with it sound too, and you can hear that when it comes up. Okay, so that is one thing that is, in addition to the vibration of the ground itself and underneath the ground, there is actually a sound that propagates with it too. Okay, so waves usually they travel in a medium. For example, if I take a rock, hold on one second, okay. Excuse me, guys. Sorry about that. Anyway, so if you take a rock basically and you put it and you throw it in a pond, you will see that the ripples start to form on the surface of the water, and that also a wave that is because okay. So what happened in that case is you have the calm water that is sitting still, and you create a disturbance. In that local point where the disturbance happened, the water goes up and down, up and down, up and down. So it's an oscillation really, but that oscillation is actually propagating throughout the entire surface of the water. If you look under the water also, there is another disturbance that goes also in the bulk of the water. So in that case, the medium is the water. For the case of sound that I'm talking about earlier, for example, and that is part of the next chapter, is it propagates in the air, and the air in this case is the medium. That's most of the time what we refer to. However, sound travels in the water too. Case in point, for example, whales and fish in general, they live underwater, and they use that for communications and to locate prey and to locate basically, to evade basically a predator. So that is actually something that is also, sound travels actually also in water too. And it travels actually in bulk media too. I mean, the walls, sometimes, for example, you're sitting in a room, although your room may have some sort of an insulation from the next door room, but you could hear the people next door. So how did the sound come through? Well, it traveled through the air in that room, then through the wall, provided the wall is not soundproof. But even if it's soundproof, there is a little bit of trail of sound that is going to propagate. So even that, you're probably going to hear some sort of an attenuated, meaning less than what it could, sound that is coming from the next door, meaning that sound in that case traveled through the wall. So sound travels through a lot of media in that case. And that is the true for all kinds of waves, provided the waves we're talking about in this case are mechanical waves. For the case of light, for example, and that concept we're going to explore down the road again, light travels in, also air travels in, for example, glass. That's why you will be able to see what's going on the other side. And then using window, for example, in your car, that's what light is coming through the window to you. But there are some materials, for example, the wall of the room is kind of opaque in that case, meaning it's similar to that insulation that you do for sound. But in that case, light will travel just a little and then drops and comes dead so that you don't see what is outside. On the other side, also, light has something peculiar to it in that it travels through vacuum, meaning lack of medium, meaning lack of matter. So that is something only unique to sound, to light, but all other waves that we talk about, for the case of sound, for example, or a surface water wave, for example, or a seismic wave, for example, or a wave on a slinky, you take a slinky and you create a disturbance on it, that also travels through the slinky. So that is, or a string, for example, you take string and it creates a disturbance on the other side, on one side, and you will notice that the disturbance travels through the string. So those are all waves. So if I ask you now, what is really traveling in the case of the string? I'm holding the string on one side, for example, of a musical instrument, and it creates a disturbance on it on one side. Is really the string moving or the molecules of the string moving from one end to the other? The answer is no. The molecules in this case, or the parts of the string, are moving left and right depending on how I create the disturbance. So if I create it left to right, then the atoms or the parts of the string are going left and right. And thus they cause their next door neighbors to also oscillate left and right. And those they cause their neighbors to oscillate left and right. So if I wait long enough, that disturbance will reach to the other side. But none of the parts of the material themselves move left to right. I mean, for the entire length of the string, I should say. They all move left along the disturbance, but not along the medium. Same thing is for sound. So if I speak, for example, right now, since I'm doing that, and you guys probably are hearing it too, what I'm doing actually, I'm creating exerting a pressure on the surface of, oh, I'm sorry, on the air immediately next to the source. And that pressure is actually going to exert a pressure on the next door and so on and so forth. And that pressure will travel throughout the entire room, among other things, as the speaker. And if you are next to me, it's your ears that is going to reach. So in that case, it's not the molecules of the air travels from one side to the other, but rather only the disturbance that is traveling. And in this case, the disturbance that is traveling, but the parts of the air are not, at least along the medium. What is going on in that case is the motion is just localized, but that localized motion is traveling throughout the medium. So this is one distinction that needs to be made between waves. Oops, I'm sorry. The screen up. And oscillations. Okay, so those are the two, the difference between them. There are two types of waves. Waves that are called transverse waves, and waves that are longitudinal waves. Because I have two possibilities. Let me explain this last 2 points. Okay, here is the idea. If you take string, for example, that was sitting like this. So this is when it's steady state, when it's undisturbed. Okay, so if I take string and stretch it and don't do nothing to it, this is how it looks like from one end to the other end. Okay, but what happened to it is I come in here and it creates a disturbance. So that disturbance is going to cause it to move up and down. So that disturbance will cause the string to move up and down, and that is going to propagate along the string. So the string at some point may look like this. Obviously, I'm continuously pumping this motion. I'm continuously dragging the string up and down to continuously form this shape. Okay, so now this is the shape of the string that I have. Obviously, in this case, the oscillations are going up and down, but the wave is traveling left to right. Is going on one side, provided in here, there are two options. It could be held in place. In that case, it's closed. Or it could be open, meaning like a whip, for example, when you're doing that, when you snap the string in that fashion. So again, that is two possibilities on the other side too. So now, this is the direction of travel, and this is the direction of the wave, the disturbance itself, or the oscillation. Both of them are perpendicular, as you can clearly see. They form a 90-degree angle between them. So this is called the transverse wave. Transverse meaning normal, meaning perpendicular. So that is, the shape for it is like this. For the case of the slinky, for example, I have two possibilities. So if I take the slinky, for example, so this is the length of the slinky. This is how the slinky would look like. Okay, what I do in this case is, obviously I could treat it like a string, and then move it up and down and create transverse waves, but that's not what I'm interested in right now. This is what I'm interested in. I'm going to take this slinky and compress this region of it. So if I compress it, this is how the slinky would look like. This region is compressed, and then the rest of the string looks like this. And then let go. So initially I compress it and then let go. So what happened is, but then I keep on doing this. Okay, keep on compressing it and letting it go. So this is how the string would look like at some, the slinky, how it's going to look like at some point. So it's going to look like, this is again the length of the string, the slinky. So at some point it's compressed and not compressed in here, and then that compression reaches a region and then not compressed and so on and so forth. Okay, so the disturbance I created, which was this side, so this is the oscillation. In every point, it's going left and right, and this is the direction of travel too. So it's going along the same side, so, and it's the disturbance is moving in the same direction. So I call this one actually longitudinal or compressional. It's the same thing, longitudinal. The word for it also that you might find when you're reading about it is a compressional wave. they're the same thing, meaning that the compressions are happening along the same side where the wave is moving. So those are the two types of waves that we see in nature. There are some combination of them. For example, the surface waves, sometimes they do both, okay? And like, for example, in a seismic wave, they have the P mode, the S mode. So there is both modes, actually, they can appear in the same thing. In other words, if you're experiencing an earthquake, you're going to see two modes. One of them is going to travel along the ground and you will feel it, and another one that is going up and down to the ground. So both of them could happen at the same time. But those are the two kinds of waves that you will have. For the case of the string, the example of the string, this is a completely transverse wave. Take string and you create transverse wave. For the case of the slinky, this is the slinky, you can do both too. You can create like this and compression at the same time. And for the case of sound, sound is actually a compressional wave. I mean, longitudinal, that's what I meant. The same thing, okay? So it's of this type. In other words, there is a compression of the air immediately next to the source, followed by rarefication, followed by, this is called the rarefication, by the way, when there is lack of compression. So this is compression, compression, and this is a decompression or a rarefication. Rarefication, meaning it's not as compressed, okay? And they follow one another, okay? Let me represent this one in space, because I can take this the string like this one, for example, and take a picture of it. Similar to the wave and how it behaves in time, but this is a localized behavior in a sense that this is only depends on time. So if I track the mass in here, it's going to go up and down, up and down, up and down, and trace its motion when it's up and then down, and when it's up and down, and that is with time. So I have a clock, and I'm sitting next to the clock and basically timing it as it goes up and down. And the same fashion, actually, I could do the same thing for a wave too. I could stay in here, and any point in the string, it doesn't matter what I would choose, like for example, this one, and this point in here, if I'm sitting on that string, or if I put something on that string to mark it, for example, with a red dot on it, I will see it going up and down, up and down, up and down. And that's what I meant by it as being an oscillation. So that can be represented also with a time-dependent behavior. But I could take a picture and freeze time in doing so and see its behavior overall in space. Same thing with the slinky. I could take a dot, for example, in here and see what happened to it. It's going to go left and right, left and right, left and right in here. And then I could describe that in time. And that's going to give me also temporal behavior, similar to the oscillation. But that's an oscillation that is moving along the slinky. I could take a picture of the slinky at any given time and freeze time and see how it looks like over space. So that's basically the distinction for waves as opposed to the oscillations. So here is the idea. So this is a given point in a wave with respect to time. So this is time, and this is how the wave would look like. So at some points it's moving up, moving maximum from its origin, then it's going to come down to the minimum, and then it's going to go. So think of somebody on a boat, for example, on the ocean, okay, way in the ocean, and there is a wave that is coming. That person is sitting on the boat will go up above the sea level and come back actually below the sea level, up and down, up and down, up and down, as the waves are coming in and out. So that is basically that bobbing motion in time. For him, he's looking at the clock. Oh man, we're going down. Oh man, we're going up. So that is basically the behavior that I'm describing in here. So in this case is the displacement. For the case of sound, it's going to be the pressure, because the air pressure changes or the air density changes. Okay. In the same time, so this distance from here to here is what we call the period, or from here to here. It's the same thing. the period t. Okay? And it's related to the frequency in the same fashion as an oscillation. Frequency and period are inversely proportional to one another. Okay? And period is measured in seconds because time is in seconds. So this is in seconds. Okay? But this displacement in the case of the string is in actually centimeters. How many centimeters up and down the string is going to go? For the case of sound, is going to be in the measurements of the units of pressure or density, whichever unit you're trying to do. For the case of light, it's actually different. Okay, we use the electric field or the magnetic field. Then again, we're coming to those points down the road. For the case of, if I take a picture of the spring, for example, or the surface of water, or the slinky, it doesn't matter. If I freeze time somehow, I can describe the wave behavior, in this case, in space. So similar to I did it with time, now I can describe it with space. So this is space, usually in meters as the unit of measurements. And then here, whenever I am measuring, for the case, for example, of the string, I'm sorry, for the case of the string, it's in centimeters, how many on and off the vertical I am for the case of the string. So if this is the horizontal direction, this is the equilibrium, how off I am from equilibrium in centimeters is 2 centimeters, 1.5 centimeters. And this one also probably less. If this is 1.5 centimeter, probably this is maybe what, 0.5 centimeter, and so on and so forth. This is actually a negative number. This is negative 1.5 because I'm below the equilibrium. Same thing in here, how off I am for the slinky, okay? If compared to its original equilibrium, because remember the slinky, this point in here was here, and now it's moving back and forth. Okay, so probably it was this one because I compressed it, so it moved all the way back. Okay, so it's this distance back and forth. At some point, it's going to stretch. It's going to move to the opposite direction because this will be compressed and this will be decompressed. So again, those motions for the case of pressure, again, is going to be the units of pressure or something for the sound. Again, it's going to be a behavior in space that is not necessarily. So again, this distance from a maximum to a maximum is what is known as a wavelength. There's two words in this word. Okay, you take two words. You have wave, which what we're talking about, and length is length. So what I mean by wavelength, it's the distance. So when I say distance, I really mean meters, okay? Distance between two consecutive maxima or minima or similar points. In other words, the distance between this point and this point are also wavelength. The distance between this point and this point, it has to be similar though, because this one we're going up and this point we're coming down. So we need to find the next point that is coming down. It's easier to remember maxima in this case, okay? So it's going to be that distance, and it's again in meters. So that is a wavelength. In the book, we use the symbol lambda, the Greek letter lambda. Greek letter lambda. Okay, it has this weird shape in here. It's like Y backward, okay? So it's like you take a Y and you flip it on its head, okay? And you write it like this, okay? So that's how it is. It's upside down Y. And when you flip it, retain the direction of the little leg of the Y, okay? So don't, I've seen it, somebody write it like this. So this is not lambda, okay? This is how the lambda is written. Anyway, so this is the wavelength, and it's the symbol lambda. So again, lambda is unique to waves. You cannot have a wavelength for an oscillation, a pure oscillation. Like, for example, it doesn't make sense to talk about the wavelength for a pendulum. It doesn't make sense to talk about the wavelength, for example, for the mass spring system. So if you're asking about differences and similarities, this is one of the differences. The similarities are both of them have periods, both of them have frequencies, both of them have temporal behavior. They behave in time in a similar fashion. They have both a similar graph with respect to time. So those are similar characteristics, but you cannot have a wavelength for an oscillation. You can only have it for waves, okay? Furthermore, a wave also has a speed. Now that is something that is also unique to waves. And I'm going to make a distinction because both of them will have another kind of speed, but that's not the speed we're interested in. Okay, let me explain this last point. Very important to understand the distinction of what I'm talking about. You might be wondering, this mass in here is going left and right, so there is a speed, and you're right, with which it's going to go back and forth. If it's going to go slow, that means it's less speed, but if it's going back and forth fast, that means I have a high speed. Same thing for the mass spring system in here. It's going to go up and down with a speed. Okay, so it's going to go probably fast and slow depending on how the frequency is. That is not what we talk about when we talk about waves. Waves also have that speed too, if you were curious. This mass, this dotted line in the string can go up and down depending on how fast it can go up and down. So there is a speed too there, but that's not what we're interested in when we come to waves. So that is not the speed. So that is a localized speed, similar to the oscillations. Same thing. This point in here that I dotted in the slinky can go back and forth with a speed. But again, that's not what we're interested in. What we're interested in for a wave is how long does it take for it to travel from this point to this point? That is speed. And that is not a material that is moving, actually. That is the wave itself moving. So in other words, this point is going up and down. That is a speed, but that's a material speed. That is something that we can measure for that point. Same thing. This point is going left and right, and that is a speed too, and that is a material speed. And that is something that is not we're interested in the case of the wave. What we're interested in the wave is this disturbance, this oscillation. How long does it take for it to go to the other end of the string? Or how long does it take for the compression on the slinky to reach the other side of the slinky? Or how long does it take for sound to leave the source and reach the receiver, the ear, for example? That is the speed we're talking about. So the speed of the wave is exactly what it is. Speed of the wave, and not as it travels through the medium, I should say, as it travels through the medium is not the physical speed of its parts, if you wish, in their oscillations. I hope I made it clear in the explanation in their oscillations that there are two things in here to take into account. First of all, there is an oscillation up and down, but that oscillation is traveling. That is the one we're referring to for the speed of for the wave itself. Okay, that is the wave. So if you're asked again, what is going on in this situation is that the wave that takes that energy that you're creating in one end up and down and putting it on the other side of the medium. So what is actually being transported in this case, in the case of the wave, is energy. So the speed in this case is the speed with which the energy is propagated. In the case of sound, it carries with it energy too. For example, if you have a big collision of two objects, the collision, both objects are, let's say, for example, moving. In the case of a car, two cars, for example, in the case of a collision, both when they collide, part of their energy is going to be going into deforming the two cars. Part of their energy is also going to heat the two cars. And part of the energy is actually gone in the form of sound. The more energy in this case, the louder the sound. The same thing in here. The higher the string being disturbed, the more energy I'm taking with me. Again, the more compression I put on it, the more energy. The louder, in the case of speech, the more compression I'm producing. So the energy is actually what is traveling in this case. So that is the energy with which the speed of the energy of that travels is the one that we're talking about. So waves carry energy in their travel. Okay, the speed with which energy travels is the wave speed. That is really the useful relationship that you have in here. Which brings me to the last point in here that we're going to explore in this lab today, and that is the speed, which is the velocity v. So the symbol is v in this case, the speed of the wave. And the units for it are meter per second, by the way, is equal to the wavelength. So lambda again is the wavelength, length divided by t, the period. Remember, I said that the wavelength is in meters and the period is in seconds, so everything fits. The speed is in meter per second, and the wavelength in this case is lambda, is actually in meters, and the case of the period is in seconds. Okay, I think I talked about the most important. Actually, I can write it differently. Okay, so we're at this point in here. I wrote it earlier differently, because 1/t is exactly the frequency. So I could sub in here and write this expression as just lambda times f. So this is the relationship that we're going to explore, which is the same thing, by the way, as lambda over t. It's the same relationship that we have as before, okay? So these are some of the ideas that are needed for the lab today. And this is the expression that we're going to do. So what you're going to do today in the lab is basically, you have a column of the water that you're going to be filling with water, and you have a bucket on the other side, and they're connected underneath. And you have a tuning fork with a given frequency. So f is given with a tuning fork. And your job is to measure lambda, okay, the wavelength. Once you measure lambda, you're going to determine the speed of the wave in this case, okay? So you're going to measure the speed of the wave in this case, okay? You're going to repeat this expression several times, and you should be able to find the velocity of sound. That's why the lab is entitled speed of sound, okay? Later on, you're going to change tuning forks. So that means each time you have a different tuning fork, you're going to have a different frequency, and then each time in that case, you should have a different wavelength. What happened in this case is that you're going to be hearing the sound that is produced, and you are going to form something which we're going to cover right now, and that is called a standing wave. So once you have a standing wave with the utmost basically intensity that is produced in the tube, then in that case you have created a standing wave. You move the bucket up and down, and you create the next mode, okay? And you measure the distance between them, and that is half a wavelength. Okay. Once you do that, you're in good shape. Okay, so let's talk about wave interactions, which is important for our next topic. Okay. Okay, if I take two waves, let's take, for example, a string that was like this initially. And if I create a disturbance that goes like this, so obviously this disturbance is going to travel. So this is left, and this is right. If I wait a little longer, this disturbance would look like this. So it's no longer here anymore, but it's rather like this. So this is how the string would look like now. And it's moving this way, okay? So this is a right moving wave. It doesn't look like it's a harmonic wave, but it's a wave nonetheless. It's a disturbance that moves along. So in other words, you create just a whip like this one and wait for it, and it's going to travel along the string. The string is stretched, by the way, so that it doesn't crumble in between and you lose that shape, okay? Now, what I can do also is actually do two of them at the same time. So here is what the idea. So here is my string that was before. So I create one on one side, and I create another one on the other side. So this one is actually going to be moving to the left, and this is going to be moving to the right. And I ask what happened when they meet, when they collide. Well, in this case, because both of them are in the same direction, when they collide, this is how the string would look like. So this is how it was. So the string in this case is going to go as high as the sum of the two. Okay, so this is the moment of the collision. If I wait a little later, they separate. Okay, the one that traveling to the right will continue to the right, and the one that is traveling to the left will continue to the left. So this was the original one that started in here, and this is the original one that started from the other side. Okay, this type of interference is called constructive interference. Constructive meaning you add them and they become more intense. Okay, so this is a constructive interference. That means they add up, they become more intense. Okay, as opposed to another type of interaction of this form. So if I create a right moving wave this way, and in the opposite direction, I actually create a left moving wave in the opposite direction. So what happened in this case, when they collide, this is what happened during the moment of the collision. If they are chosen the right intensity, if this intensity, this height, that means this distance, and this distance are the same, that is what the intensity of the wave is and how loud the sound is, basically. If they both of them have the same intensity, this is the moment of the collision. They're gone. So as opposed to constructive interference, this is called the destructive interference. There is no more. But if I wait a little later after the collision, when the two emerge, again, they will emerge. This was my original right. Sorry about that. Do you guys hear me? Okay, thank you. Thank you, guys. I don't know what happened to the camera. Sometimes things like this happen and I lose all kinds of connections. I don't see myself on the camera, so I suppose the camera is still not coming up. I don't know what happened. I don't want to unplug it right now. So the point being in here is, let me go back and share the screen again. Just please confirm to me that we get at least to this destructive interference. Yes or no? You can speak up if you can. I think I can hear you. Yeah, okay, very good. So basically, this is a destructive interference. So this is how the string would look like. Let me get this thing out of the way. So this is how the string would look like. I may have to close that too. Okay, so this is how the string would look like. And at the end, they emerge in such a way. This was my original right moving wave. And this is my left moving wave. So they emerge in the same fashion from the collision too, although they went through destructive interference, provided they are chosen with the proper amplitude. You ask, what happened if I don't choose the right amplitude in this case? Well, in this case, there will be a little bit of bump up or down, depending if this first one, the right moving one, is up slightly more or less than the left moving one. So that is basically what a disturbance. Most of the noise cancellation systems use this similar fashion. For example, in the case of the airports, they know more or less exactly the frequencies that are being generated by the airplanes. So they created corresponding waves that are in the opposite direction to cancel that noise. Okay, that's probably in the case of airports. If not, then you use white noise. If you know your station, what's the frequency that's choosing to emit, then you're going to create a wave to cancel that. Okay. For some reason, my camera is not coming up and it looks kind of strange, okay? Sorry about that, guys. Anyway, and it's on. So let me try to turn it off and turn it back on. No, still not showing. Sorry about that. Anyway, so those are the two types of interactions that you see in the case of constructive and destructive interference. So which brings me to another point in here, and that is if I take a string in here, which we're going to need for the lab today, by the way, and I fixed from one end, okay? and it created disturbance in here continuously. So this is basically disturbance. Like, for example, if I have a frequency that is going up and down, in this case, like vibrations up and down. So in this case, the string would look like this as the wave is going to the other end, okay? But in the same time, in this case, there would be a reflection, and the reflection, because this end is fixed, is going in the opposite direction. So the wave in this case will have this shape when the two waves meet. Some points, like this one in here, and this one in here, and this one in here, there will be destructive interference. Destructive interference, meaning the string is not moving, okay? This is called actually a node. And some points like this one, and this one, and this one, and this one are actually maximum displacement. Those are constructive interference. Okay, so these are NT nodes. Are you guys looking at my shared screen, or are you still looking at the camera? Because I'm kind of confused a little bit with the way situation that is going on. Are you looking at the one notes or the camera?
We're seeing the notes.
Okay, very good. Thank you very much. Very good. Anyway, the point being in here is that this is an NT node. This is a node where there is constructive interference, a maximum basically displacement. That is actually in a node. I mean, if you guys have played with this one in here, especially in the musical instrument, this is exactly what you form, what you make, okay? You create nodes and NT nodes. The 2 points in here are nodes by the default. So this is actually a node also. And this is also a node. So you ask, how many nodes do I have? Count them in this situation. I have 1, 2, 3, 4, 5 nodes. How many NT nodes I have, including the ends? So I have 5 in my example, 5 nodes. The ends are included. If you don't include the ends, of course, it's only 3, okay? But if you include the ends, which typically you do, then in this case, you have a 5 nodes. You ask how many NT nodes you will have 4 in this situation, because you have 1, 2, 3, and 4. So there are 4 NT nodes. Okay. How about if I do it differently? How about if I only have like this situation? This is fixed, but I only have this much. I only have 2 NT nodes, if you wish. Then in this case, I will have 3 nodes. 1, 2, and 3, because I have 1 and 2 NT nodes. So always the number of NT nodes the bulges, if you wish, if you want to call them that way, NT nodes, is 1 less than the number of nodes, and I'm counting the ends included. This is a fixed string. There is another kind of string that you could do, and that string where you don't fix the other end. You take a string, for example, in here, that is again similar to the first one, but it's not fixed from the other end. So in this case, you could create, for example, 1 disturbance and then half a disturbance. This end is going to go up and down. And again, the reflection in this case, as it's going up and down, is going to create a returning motion. And the string would look like this. Now, if I count how many nodes in this example, I have 1 node, 2 nodes, 3 nodes. If I count how many NT nodes, I have 1, 2, and 3. So when the ends are open string, the number of nodes and NT nodes are the same, provided one end is fixed. Okay, so kind of a little bit more details in it. Okay, interesting thing in here to note is this distance, remember, from here to here, this is actually a wavelength. This whole thing is a full wavelength. And in this case, it's actually the length of the string too. So actually from from node to node, it's only half wavelength. This is the half wavelength. In other words, wavelength. In other words, this distance is lambda over 2. And the same thing in here. This distance from here to here is a full wavelength. And this distance from here to here is another full wavelength. So the length of the string in this situation is 2 times the string length is 2 times the wavelength. And again, if I take just from node to node, it doesn't matter which nodes I consider, like this 2, for example, this is actually a half wavelength. This is still lambda over 2. Okay, so these are some of the characteristics. We call this situation a standing wave. For the case of sound, in the case of the tube, you could create it in a similar fashion. So for example, if this is a tube you have in here, you could create a sound in such a way that the sound will have one node and one antinode. So this is the intensity of the sound in this case. So this distance is just half a wavelength. And this is what we're going to do today in the experiment. Because this end is open, this is similar to this situation of the string here, except that I created only one of them. Okay, I could do the same thing for another one where I have the same opening, but again, now I could create a different frequency that could create like this. Again, I have to be careful in here in my drawing because I have to have it open from the other side. And as I'm going up again, so in this situation, again, I have how many antinodes? I mean, nodes themselves. First, I have 1, 2, and 3 nodes. And then I have 1, 2, and 3 antinodes. So the number of nodes and the number of antinodes are the same, similar to this one. As a matter of fact, this is similar to what I did earlier with the string. Okay, so this is identical. Again, the distance from here to here is only half a wavelength. And this is another half wavelength. And this is another half wavelength, for a total of 3/2 half wavelengths. 3 half wavelengths, I should say, or 3/2 wavelengths. Okay, so again, this is the experiment that we're going to be doing today. For low frequencies, you're going to have difficulty producing higher nodes, but for higher frequencies, you should be able to produce more nodes. So this is again what we're doing today in the experiment later on. Based on the measurements of your wavelength, you should be able to find the speed of sound. Okay, so again, this is the standing waves that we're going to be doing today. Any questions so far? I know it's a lot of content, but I'm assuming that you guys are doing a lot of reading on these materials in your per instructions on Canvas, basically, because Canvas is giving you pages that you're supposed to be reading, and also covering the materials on them and doing the watching the videos and doing the samples and things like that. Any questions? No? TJ, were you saying something?
Should we bring our computers to the lab today?
No, you don't need to bring your computers. You will be given the lab manual today. And we also will have a chance to go to the STEM Center and see what they do. And then we will do our lab today, okay? You will also be instructed on how to do the lab report also. Good. Thank you for the question though, okay? Okay. But this is the ideas basically that are covered today in the lab. So I want to make sure that we go through them before we go into the lab, basically blindfolded and not knowing exactly what are we supposed to know, at least up front. I know the lab may sound a lot easier than what I'm talking about in here because of the fact that you will see that it's kind of repetitive, but once you get the hang of it and you find the different values, then you should be in good shape. But remember, the relationship at the end of the day that you're supposed to be doing is this V equal to lambda times F. The velocity of the wave is equal to the wavelength, lambda times the frequency of the wave. So this is a relationship that we're trying to use and basically explore today in the class. This has a name, actually, if you're going to really read through these things and everything. It's called the Dispersion Law, okay? And we're going to come to this one actually also for light, and we're going to see this one a lot somewhere else too, except for the case of light, the velocity in this case is going to be the speed of light, okay? So these are some of the ideas that are covered in here. Let me stop sharing right now, this one in here, and let me share with you another point in here that I also included actually on Canvas for you guys. And that is actually from unit 16, chapter 16, I should say, okay? And in chapter 16, we're going to explore more the sound per se itself, not the waves in general. And we're going to have the nature of sound, the origin of sound, sound in the air, and how fast the sound is. You'll be asked this question in the quiz, so try to remember it's about 343 meters per second to be more specific, okay? But in the water, it's going to be over 1,000 meters per second, so it's a lot faster in the case of sound, okay? They should be on Canvas. Are you on Canvas right now? Let me show you that, okay? The question was, where do we find the resources on the videos, okay? So let me first of all find the link in here. That's a good question because I did not go through Canvas today to show you what's supposed to be. So let me go back home in here. And let me go to the models and let me put it in student view because there are a bunch of other things that are kind of in the way, actually. Okay, so let me stop sharing that screen and let me share with you this screen. So again, the learning objectives in here, the topics that we're covering today, here where it says sound and hearing content videos. So if I click on it, okay, it gives you, first of all, a summary of the things that I've been talking about, including this dispersion law, okay? And then these are the videos. This video is 3 minutes and 45 seconds. This minute is 3 minutes and 44 seconds. 5 minutes and 16, as I was saying, one of them is slightly more than the others. And this one is 4 minutes. After you finish that, you're going to take the quiz. Does this answer your question? Okay, very good. Very good. So that's actually a good question. There is also another thing. So let me stop sharing that. Let me stop sharing. And let me actually do something in here too, because that question is still, what happened? Let me leave the student view. Let me go to the home again. So it's all under week 2, okay? It's all under week 2. And the reason why I had to, let me first of all switch to view again and share with you the screen. Share. Okay. So if I share the screen in here, so there is the, this is where the recording of today is going to go. So that's, I don't know if that's also, I think it's very helpful to go through the recording today also, especially for the lab and even for the doing problems and things like that. This is the discussion I was talking about. This is the PowerPoints that I'm sharing with you right now that I was actually sharing with you a few seconds ago. And also, so there are more resources to use. So part of the learning objectives, if you open it, is to go through this concepts in here. And let me go back. And so this is the instruction. So it tells you specifically what pages in the book you're supposed to do. Okay. Pages 330 to 334, which is kind of 4 pages only, but that's actually all of the content that's relevant for the discussions today. So I'm hoping that, don't forget that from the previous week also you have other readings that you're supposed to do and the assignments in there too. You have the discussion that is in here, but there is another thing in here. This is where the lab is. So I want to, right now it's locked. It's going to open at 12:45. when we have that. So the time when it comes to it, we will discuss it. We'll discuss it live. Actually, we'll discuss it in person today at in the lab session. So, and I'm going to open this very same window actually and share it with you and show you exactly the instructions and the rubric and how the lab is going to be graded, and also how we are supposed to submit your reports. Okay. So again, that's a good question because I did not really share with you they have the due dates on them too, Mayali. So when you open them, they should tell you exactly when they are due. Okay. Some of the assignments, like the video quizzes, yeah, I think they all have due dates. Okay, but some of the assignments may not have due dates, and you still have them kind of open, so you can take your time to do them. But most of the assignments have due dates. Like for example, the lab reports, I know it's usually due a week later. Okay, again, since we're talking about the lab, we're going to talk about it later on. Hold on, guys. Sorry about the noise, guys. I have people in here today and they're making all kinds of noise. Okay. Anyway, let me go back into the PowerPoints. Yes. So let me share with you. So these are some of the concepts that we're going to be covering. Again, I'm going to go briefly on them, understanding that you guys are going to do a little bit of reading in here. Okay. Again, sound is a form of energy that exists whether or not it is heard. So that's saying about the tree in the forest is nonsense. Again, sounds are they're produced with whenever there is a mechanical system in here involving the motion of one object versus the other. Usually, that is where sound is made. Okay. Again, the vibrations that is usually that propagates in space. That is really the how sound is. For the case, for example, of the mouth, you of course you have all kinds of moving parts in here. The purpose of which is just to create that disturbance. Okay. Frequency is called the pitch actually for sound. Okay. So you hear people talk about pitch, high pitch, low pitch, and things like that. That is what they talk about when they're talking about it. They're referring to frequency. Okay, for sound, it has this kind of unique thing. And again, because of the music connections in here, okay, there is a lot of applications in here. Our ears, they hear anywhere between 20 hertz, which is a kind of very, very high, I mean, very low frequency, I should say, extremely low frequency. Extremely low frequency. 20 hertz is a very, very low frequency pitch. And then 20,000 hertz, which is a very high frequency. So if you, I mean, typically, usually young kids, they have high pitches, high frequencies, and as they get older, at least the hearing part of it starts to deteriorate with time, so that their range of frequency actually shortens a little bit from the high end, okay? And again, some people, they have different, so this is on average, okay? This is what a human being can hear, okay, in general. So that is a normal ear. Infrasonic waves are the ones that are below 20 hertz. Ultrasonic waves are the ones that are above 20,000 hertz. Ultrasonic waves actually are used for, among other things, for example, in medical research and actually in medical surgery also. So they have all kinds of applications in real life. Again, so again, disturbance creates a compression in this case that can move the air in here. So again, the air near the door when it opens moves back and forth, but that motion back and forth will translate all the way to the left in this case. Okay. For the case of sound, again, these are called the compressions. Did I misspell RFK? I think I did. Rarification. Sorry about that earlier. Okay. Yeah. These are compression and these are decompression zones. So the air never really leaves from one end to the other. So what's going on in this case, it's the wave that travels from one end to the other. The air moves left and right, but it's only in that local region. Same thing in here, left and right. Everywhere you look at it, it's the same thing, but it's left and right, this compression that travels. And as it travels, it leaves behind the decompression, compression, decompression, and so on and so forth. This is a tuning fork. And this is an opening of a tube, in this case, that contains air, okay? So again, this is how the waves are propagating. And in here, they're converted into an electronic signal. And that electronic signal has these characteristics again, for the wave properties again. So sound travels through all kinds of media. So hopefully you guys can get that. On average, so again, these are typical examples in here, okay? You watch a person chopping wood and note that after the last chop, you hear it 1 second later, so how fast it's moving. Of course, the distance is 330, the time is 1 second, so it's gonna be 300 and how far away is the chopper? So in this case, 300, that's the wavelength, okay? So again, these are the questions that I'm hoping that you guys can review them. And simple algebra, divide by 2 or multiply by 2 in this case, okay? One thing I did not discuss in general for waves, they have this property of reflection. Similar to light, for example, when you stand in front of a mirror, the person in front of you, which looks exactly identical to you and does exactly what you do on your hand, if you raise your left hand, that is when that person on the other side raises their right hand. But other than right and left, everything is identical to you. That is your reflection. That too is true for sound too, okay? So that is typical for waves. So when they hit a medium that separates a medium of propagation from a medium, in this case of the insulation, they reflect. There is a law that we're going to explore more in optics than here, and that is the law of reflection. The incident wave and the reflected wave will always make the same angle with the normal to the medium. This is called the law of reflection, okay? Again, these are in the case of sound. And this is a musical hall in here where you use acoustics and their properties with respect to reflections, as you can see from the ceiling in here, what they put in here, to better distribute sound throughout, okay, and make that reverberation. Sound, of course, travels in the air, and depending on the temperature of the air, then in this case, is going to be bent one way or the other, depending on how the reflection is in this case, okay? Similar to a mirage for the case of light. So in the case of cool, so this is a refraction actually, because there is a separation of media depending on their air density. So what is a refraction? Refraction, if you take, for example, a pen and you dip it in a cup of water, clear cup of water, you will see that the pen in this case is broken. So that is a refraction. The air, the speed of light, the light travels in different media, in this case, the clear cup of water, and the air with different speeds, and it looks broken. And the angle of refraction in this case and the angle of incidence are related to one another depending on how fast the light travels into the medias. Same thing for the case of air in this situation. There is a cool air and warm air, and sound travels with different speeds and is going to be refracted, okay? And it's going to be refracted toward the cool air. So for example, if it's at night, what is it? The air is cooler, and vice versa during daytime, okay? The laws of reflection and refraction has a lot of applications, whether in nature or medicine or men mind, okay? I was talking about earlier about how it's used in medicine, and it's actually used for the case of light too, okay? And in the case of also life, for example, living organisms, for example, you have dolphins using sonars to orient themselves in the water and basically find prey and avoid the predators and move around and do what they need to do. One thing we didn't talk about, and that is forced oscillations. In the case of the string, for example, when I was giving the example up and down, that is a forced oscillation. But forced oscillation has something that has to do with the let me go back into my example earlier, okay? For the string in here, in general, okay? It doesn't have to be a string. Let me go into my notes in here. Every system, even the mass spring system, has its own frequency, and the frequency we saw it to be in that case 1/2 pi. Let me write the period. The period is 2 pi square root of m/k. And the frequency in this case is going to be just 1/2 pi square root of k/m. So this is called the natural frequency. If there is wind, or if you decide, for example, to force it to move up and down, you yourself, okay, you hold it from one end and you start moving up and down, or force, it doesn't matter, air or wind or whatever causes it to vibrate, this is actually a forced oscillation. So in addition to its own oscillation, there is a forced one. And its forced oscillation could have its forced frequency. Forced oscillations, frequency. So the two frequencies may or may not be the same. This frequency on this frequency may or may not be the same, depending. If they're not the same, there is no harm in it. Usually there is no problem. But if they're the same, in this case, we have resonance. So we have resonance when the natural frequency equals the forced frequency, the forced oscillations, the forced, frequency. You know, I guess you know what I'm talking about. You have two things in here, okay? And these two things basically result, they have two different frequencies. If the two frequencies are the same, we have a case of resonance. Why is resonance important? First of all, resonance can have damaging things in nature. For example, the Tacoma Bridge, when it fell because of the resonance. The Tacoma itself, a bridge, has its own natural frequency, and the wind was blowing left and right. And as the wind was blowing, it came with a frequency that is equal to that of the bridge, and the bridge starts to oscillate violently, because this is what happened when you have the two frequencies the same. So as it's going down on its own, you're pushing it down also. So the amplitude will be higher. As it's going up on its own, that is the natural frequency, you're pushing it up. So they're equal in this case. So again, you're pushing it more than it should be. So in this case, in the case of resonance, usually the amplitude is higher. Amplitude is higher. That's why it's maybe either useful or harmful, depending on the situation. It could be useful or harmful, okay? Depending on where you want to go with it. Here is the thing. In the case of this situation, for example, this is the first time around. You push it more than it should go, and you push it further than it should go. And you next time around, you do the same thing. So the amplitude is getting higher and higher and higher and higher until the system breaks, until the system cannot tolerate that anymore. Same thing would happen with the bridge. So the bridge, every oscillation, it was forced more than it should go until the whole bridge came down. So that is actually similar to what the high-pitched singing ladies do to break glasses too. So sometimes resonance is not good, but sometimes it's actually useful. Let me give you at least one example of when it's useful. Your station, for example, your favorite station is broadcasting at a given frequency. So this is your frequency of the station, radio station. Your radio actually is tuned for this frequency. So this is your radio. These two are not equal. So in this case, you're not going to receive your favorite station. But if you tune your radio so that its frequency is in sync with your station, then in this case, you have resonance, and your radio can receive the signal at its highest amplitude. You can amplify it further, and you're going to enjoy what you're listening. But if the two frequencies are not the same, then in this case, I don't have resonance, and you're not going to get this signal at all. Your radio is going to only get the static, and it's not going to capture that signal, no matter how much amplification. Even if you turn on the radio all the way up, you're not going to capture that sound. So resonance sometimes can be useful in the case, for example, of radio tuning or receptions, and for example, signals from outer space, trying, for example, the Hubble telescope trying to analyze do spectroscopy for different kinds of planets or things like that, it uses resonance, as a matter of fact. And the same thing, sometimes resonance is actually not a useful thing to have, okay? Anyway, let me see. I know we still have about less than 10 minutes to cover. Here is the Tacoma. I'm sorry, I'm not even sharing the screen. Let me share the screen first. Here is the Tacoma Bridge, as I was talking about in here. And this is a famous example on how it fell because of resonance. Again, we talked about interference. This is reinforcement or constructive, and this is cancellation. This is true for sound, and it's true for all of that. When waves interfere constructively, I will have brighter spots, and when they interfere destructively, I will have darker spots, and they form unique patterns called interference patterns. So this behavior is unique only to waves. Particles cannot do that. So this is something that's very important. And again, it's true for compressional waves too. So the rarefication, so when you add two waves, they will be more rarefied and more compressed when they were compressed, okay? Or in this situation, in the last picture in here, we'll have destructive. You will lose all kinds of compression and decompression altogether, okay? So this is, again, some of the things that we talked about it. One of its applications is for what we call it, the noise cancellations and things like that. Okay, so these are some of the topics. Let me leave some more examples. I know we didn't talk about beats, and we're going to talk about beats on Wednesday, and we do some more examples on Wednesday when we meet. And we make sure that we finish chapters 15 and 16, and then start some of the ideas from the next chapters. Sorry about the problems with Canvas today. For some reason, I probably will have to restart my computer and see if that's going to fix the problem. Okay, I will see you guys later on today. Sounds good?
Yes.
Okay, very good. Thank you, guys.
Bye. See you later, Professor.
Bye. See you guys.